Okay, good morning everyone and welcome to number 2, the second webinar of Next Gen Road Fuels webinar series. This morning we're going to hear from our speaker Gonzalo del Alamo, who's working with the Syntef research team, and he's looking at the cost analysis and of biofuels produced from HTL of urban waste. So this morning we're going to hear about really how much is it likely to cost if we use urban waste to produce our diesel and other road fuels. It's quite an interesting topic because we've seen now how expensive our petroleum-based petrols are. So we're hoping that Gonzalo has some good news for us for the future. Okay, so before we hear from Gonzalo, I'll just give you some housekeeping rules. Remember to keep yourself always muted. If you have any questions, please use the question and answer box that you can find, I think, at the bottom of your screen. If you want to say hi or have any technical issues, please use the chat box. But for any questions, please use the questions and answers box. And then those questions will be asked to Gonzalo at the end of the presentation. So I think that's all for housekeeping. The floor is yours, Gonzalo.
Okay, thank you, Emma. So I will share my screen with my presentation. Share. Yeah. Okay, Emma, can you raise your hand?
Perfect. You can see everything. Great.
Yeah, good.
Go for it.
Yeah, okay. Hi, everybody. First, thank you very much for attending this webinar. A few words about myself. My name is Gonzalo del Alamo. I have been working for the last 10 years at Syntef Energy Research as a research scientist. And my main interest as a research scientist is being on developing technologies for sustainable production of energy, and also utilization and recycling of waste fractions and residual biomass. And actually this project, the Next Gen Road Fuels, is kind of a combination of both. So it's been a real pleasure to work in this project. And then a little bit about the role of Syntef Energy in the project. We have been working in a work package, which is called the Technology Scale Up and Costing, where basically we look at the overall process and then we analyzed both the process itself and also the cost of producing biofuels from urban waste. And this is going to be the topic of this presentation. This is an outline of the presentation that I would like to give today. First of all, I would like to give a brief introduction, mainly saying a few words about the objectives, general objectives of the Next Gen Road Fuel project, and also, which is important, the approach that we have taken in this project to do the techno-economic analysis. And then there will be two main sections in the presentation. The first section will focus on the decentralized production of biocrude from HTL of urban waste. Here I will use much time to look at the process design, and also I will present the main result for the cost of the biocrude. And then there will be another main section when we will look at the upgrading of the HTL biocrude based on refinery processes. Again, we will look at the process design, and also I will give the final results of the minimum fuel selling prices we have obtained. Then will be some brief conclusions, and then I will give the opportunity to you to give some questions. A few words about the Next Gen Road Fuel project objectives. So basically, the project's aims to produce market fuel, road fuels. In this case, will be gasolines and diesel from what we call aggregated urban waste. And aggregated urban waste are different main fractions of waste that one can find in cities. In this case, the three main fractions we have considered are sewage sludge, bio-waste, or the organic fraction of municipal solid waste, and then waste wood. And then looking at the overall process or the overall value chains, so there are two main aspects in the overall conversion. First, we consider the conversion of the feedstock to what we call a biocrude, which is an oil phase intermediate product. And this is done in a decentralized plant where the main technology here is the hydrothermal liquefaction at supercritical water conditions. Part of the HTL plant or includes the separation of both nitrogen and phosphorus from the feedstock. And then the biocrude produced from the decentralized HTL plant is upgraded to final marketable biofuels at a centralized refinery, so based on conventional refinery processes. I wanted to include here, which is important for looking at the overall process design, the main targets that we have aimed in this project. The targets are on the energy conversion. We aim to have 85% of the energy conversion from the feedstock to the final biofuels. We have phosphorus recovery of 95% and nitrogen separation before the hydrothermal liquefaction process of 80%. We have considered the analysis, particularly the cost analysis of this technology in a scale range between 30 and 300 dry tons per day of the HTL plant. And finally, we have a goal of achieving minimum fuel selling prices for the road biofuels that we are producing below 15 euros per gigajoule, which is pretty much equivalent to 0.6 euro per liter. Yeah, so then I will present later how far or how close we are within these targets. Okay, so I will try to, yeah. Okay, approach in techno-economics. So this is the approach we have been using in this project. And also this is the typical approach that we at Sintef Energy Research follow to do techno-economic analysis. Here, what is important in techno-economic analysis is to actually achieve some realistic results for the final cost of the biofuels produced from the overall technological route that we propose. And then this includes some important aspects to consider. The first one is on the process design. So it's really important to develop a quite realistic and detailed process design that also include technologies in the integrated process that are feasible. So then it's important to really spend time defining the overall strategies for the process design and also do a good selection of the technologies that will be involved in the overall process. Then once we have these strategies and maintaining technology defined, so we can describe different scenarios through what we call process block diagrams that shows somehow the integration of the main different process involved in the overall conversion. And then once we have that, so we go ahead and we look much more into the details of the process design, and then we identified individual main process equipment, but also auxiliary equipment, and we developed what we call detailed process flow diagrams, which actually so they are engineering flow sheets. And this aspect is really important because it's essential to capture in the process design all the details, particularly on the equipment, both main process equipment and also auxiliary equipment, to be able to do a realistic cost analysis. Also, last but really important is to include as part of the development of the process design a good analysis of the risk, and then include mitigating measures of the risk that should be included in the process design. So these are the main or the essential aspects in the techno-economic analysis that can lead to some realistic calculation or estimation of the cost. Then on the analysis itself, the approach that we follow at SINTEF is to combine the process, the scale up, the equipment scale up, and the cost analysis through same parametric models or combined parametric models. And this is the approach we have been using in this project. Okay, so then I will talk about the production of HTL biocrude. This is a decentralized production of HTL biocrude, and for this biocrude production, we have considered 4 different scenarios. In this slide, I am presenting what we call the baseline process design. The baseline process design is the simplest design that you can have to be able to produce biocrude from the feedstock. This process design mainly is based on the existing commercial technology of Steeper Energy, which Steeper Energy is an industrial partner in this project. But this proprietary process design has been modified in the project to be able to process urban waste. And then looking at this overall baseline process design, so we have main aspects that I will highlight. First, there is a preheating. There is a heating of the feedstock before mixing with the catalyst in what we call a slurry preparation. This is an important aspect in the design because we need to heat up the slurry before being pumped, mainly to reduce the viscosity. Then after the slurry preparation, there is another heating to be able to reach the supercritical water conditions for the HTL process. And then there is the conversion of the feedstock in the HTL reactor, basically to produce the biocrude. The product from the HTL process mainly contain 4 different phases, which are the oil phase, an aqueous phase containing dissolved both organics and inorganics. There is a solid residue, and there is a gas phase. So these four phases are separated with depressurization and cooling. And then in this separation of phases is very challenging when we consider the conversion of urban waste to biocrude. So, and then I will present some features of the design in the next slide. One of the problems that we found in the separation of phases is the actually high content of ammonia in the aqueous phase, and this cause problems later in the process water treatment. Then, as part of the phase separation, there is a flushing using air of the aqueous phase to be able to separate the ammonia. Then the aqueous phase, after stripping of the ammonia, is taken to the water treatment. The water treatment here is based on distillation. Particularly, the technology that we consider here is mechanical vapor recompression, where we separate clean water that is disposed, and then there is a concentrate from the water treatment that both what can be recirculated back to the HTL process, but also there is some part of this concentrate is bleed and is considered as a part of the solid residue. So from the phase separation, also there is a solid residue which is taken directly, is disposed directly from the plant. The gas phase, which contains acid gases and light hydrocarbons, is used for combustion and recovering of heat that is used back into the process. And the remaining flue gas after combustion is clean. There is first a reduction of the NOx through selective catalytic reduction, and then there is further separation of acid gases using a dry scrubber. This slide shows the level of detail that we have considered in the process design, and this is just an example that is an example of the phase separation of the HTL process. As I said before, the separation of phases after HTL is very challenging. It's been one of the main challenges in this project, and then basically it requires a quite complex process design to be able to separate the different phases. Basically, this phase separation system contains first depressurization based on a capillary system. There is, after the capillary decompression, there is a separation of the gas. And then after gas separation, what we obtain is an emulsion of the aqueous phase, the solids and the oil, which are very difficult to separate. And then the separation of this emulsion is being achieved in the project by a multi-stage centrifuge system. The first centrifuge, we achieve about 50% separation of the aqueous phase from the emulsion. And then after the first centrifuge, there is a need for using a chemical solvent under low pH conditions to be able to separate the oil, basically the oil phase from the aqueous phase. And then there is a second centrifuge where we achieve the separation of both the oil phase from the aqueous phase, and also separation of the solid phase. This is a second scenario. Sorry, I forgot to say that in this simplest baseline process design, we have not included any separation of nitrogen from the feedstock, and we have not included any recovery of phosphorus. This is a second scenario where we include the recovery of phosphorus in the baseline process design. The main strategy for separating phosphorus comes from the fact, and this has been measured experimentally, comes from the fact that most of the phosphorus contained in the feedstock ends up in the solid phase after the phase separation. We are talking about around 95% of the phosphorus ends up in the solid phase. Then the best approach or the best strategy to recover phosphorus is is to separate it from the solid phase through leaching of these phosphorus at acid conditions, and then precipitate the phosphorus as estrubite using ammonium present in the aqueous phase, and also magnesium. Then after the precipitation of the estrubite, there is a dewatering system where the estrubite is dewatered and separated, and the remaining aqueous phase is taken back to the process water treatment. And there is a third scenario where we introduce both separation of nitrogen from the feedstock and phosphorus recovery. This is achieved before the HTL process. And here, in this scenario, what we include is a thermal hydrolysis of the feedstock. This thermal hydrolysis is at around 120 degrees, 120 Celsius degrees. And then at these conditions, we can achieve a high solubility of the nitrogen and also high solubility of phosphorus and metals. The nitrogen that is dissolved in the thermal hydrolysis is mainly in form of ammonium ions, and then the separation of the ammonium can be achieved after the thermal hydrolysis through air stripping. And then this air stripping with the separated ammonia is taken back to and mixed with the combustion air. Yes. Then after separation of the ammonia, there is a filtering where the retentate of the solid fraction from the filtering is taken to the HTL process. And then the liquid phase contains solubilized phosphorus, and then this again phosphorus can be separated in form of estrubite through precipitation. There is a fourth scenario where we also include the separation of nitrogen and recovery of phosphorus. In this case, is based on an enzymatic pretreatment. This enzymatic pretreatment includes two-phase hydrolysis, and this phase hydrolysis use milder conditions as the scenario that I presented before, only with pure thermal hydrolysis. In this case, when we consider enzymatic hydrolysis, the temperature that we can use are lower, it's around 50 degrees, but there is a need, before the enzymatic hydrolysis, there is a need to include also a mild thermal hydrolysis to improve the performance of the enzymatic hydrolysis. In this case, the nitrogen is solubilized in the aqueous phase in forms of amino acids and peptides, so it cannot be separated. It cannot be further separated from the aqueous phase. But we can achieve, even we use lower temperature, we can achieve high solubility of the phosphorus also. And then this phosphorus can be separated in the same way as I have presented before, is through precipitation of the estrubite. But in this case, the nitrogen that is part of or solubilized in the aqueous phase, as I said, cannot be separated and has to be taken to the water treatment. So I will not go into the details of the analysis because we don't have time in this webinar, but I will just present some highlight results. This is a table presenting the main process performance of the 4 different scenarios that I have been describing before. We can see that the highest energy conversion efficiency that we can achieve is in the baseline process design, which is around 58%. this is the conversion energy from the feedstock to the biocrude. Yes, and in this case, for the baseline process design, there is a net heat demand per unit biocrude energy of around 25% approximately. Considering the recovery of phosphorus from the baseline design, or separation of the phosphorus from the solid residue of the HTL process, we can see that we can achieve around 60% of the phosphorus recovered. Then for the separation of nitrogen, we can see that is the thermal pretreatment that performs the best. And here we can achieve 50% of the nitrogen containing the feedstock can be separated in the pretreatment. Yes. So I will. Yeah, so I will just go to the main result. This is the levelized cost of biocrude. The levelized cost of biocrude. These results of the levelized cost of biocrude are presented in euros per liter. The levelized cost of biocrude include both all the capital cost and also the operating cost. And then in this plot, we can see the result for the baseline design, which is the solid line. This is the baseline design achieved the minimum levelized cost of biocrude, which is ranging between approximately 1.4 to 2.3 euros per liter. And this variation has been considering a capacity of the biocrude production plant in the range of 30 to 300 dry tons per day. As we introduce in the baseline design the phosphorus recovery, the increase of the biocrude increases approximately by 20%. Basically, the increase of the cost when we include the phosphorus recovery comes from the fact that we increase the volume of water in the leaching process for the phosphorus recovery, and then this increase of the amount of water, the amount of processed water in the process leads to a higher cost in the water treatment. If we include, in addition to the phosphorus recovery, if we include nitrogen separation, then the cost of the biocrude increase further. Is the pure thermal hydrolysis that leads to the lowest cost of biocrude compared to the enzymatic pretreatment. And then when we consider the thermal hydrolysis, the increase of the biocrude, of the cost of biocrude relative to baseline is around 50%. And then for the case of the enzymatic hydrolysis, the increase of the cost of biocrude increases by 70%. Again, the main cause of the increase of the cost of biocrude is due to the increase of capital costs in the pretreatment, but also the increase in the amount of processed water produced in the overall process that leads to a higher cost in the water treatment. This is a distribution of the cost of biocrude considering the baseline process design, distribution of the main contributors, to the biocrude. We can see that operating and maintenance costs actually doesn't contribute that much to the overall cost of biocrude, and actually they are compensated but the income that the plant gets by processing the waste. What is contributing the most is actually both the capital cost, or the cost of the equipment, but also the cost associated with the development and construction of the HTL plant. Yeah. Now, the second part of this presentation will address the upgrading of the HTL biocrude to market both diesel and gasoline. This upgrading is based on conventional refinery processes. Basically, this process block diagram shows the overall upgrading process design. Basically, there are two main parts in the upgrading process. The first one is multi-stage hydrotreating of the biocrude. This multi-stage hydrotreating, there is two main phases. The first one is what we call the gas reactor, where the main goal of the gas reactor is to separate inorganics from the biocrude. And then there is a second stage, which is a proper hydrotreating process, where the main goal of this hydrotreating process is to separate nitrogen, sulfur, and oxygen from the biocrude. After the hydrotreating, there is a separation of phases. First, there is a high pressure separation, where we separate from the biocrude mainly light gases and water. And then after the high pressure, we have a lower pressure separation, where we mainly separate some light hydrocarbons gases or light hydrocarbon vapors from the oil phase, and then from the low pressure separation, or the oil from the liquid oil from the low pressure separation is taken to fractionation in a distillation column, where there is a fractionation to naphtha, middle distillate, and heavy distillate. The naphtha range from the distillation is what we assume that will be further converted to gasoline, and the middle distillate is considered to be representative of a diesel range. The heavy distillate from distillation is further processed in a hydrocracking unit, and then in the hydrocracking unit, the heavy distillate is converted to further naphtha and middle distillate, which is taking the product from the hydrocracking is taking back and mixed with the product from the hydrotreating before separation. These are the results of the minimum fuel selling prices that we can achieve. These minimum fuel selling prices consider both the production of biocrude and then the upgrading of the biocrude, and include all the capital cost and operating and maintenance cost from the feedstock, from the urban feedstock to the biofuels. These results of the minimum fuel selling prices are as a function of the capacity of the upgrading, which is between 7 and 70 tons per day. This capacity range is equivalent to the 30 to 300 dry tons per day of the capacity range for the HTL biocrude production plant. In this plot, we see the solid line is an average minimum fuel selling price in this capacity range, which are between approximately 1.9 and 2.7 euros per liter. And then the dust line, the lower and upper dust line are a minimum and maximum values of the minimum fuel selling prices when we consider some ranges both in the operating and maintenance costs and the capital cost. So we can see that if we consider some optimistic scenario, the minimum fuel selling price that we can achieve is between 0.9 and 1.4. But in a worst case scenario, so the minimum fuel selling price achieved is quite high, is between 3.5 and 5.7 euros per liter. Yeah, so then some main conclusions to this presentation, and these are the key main results from the analysis. We can see that through the process that I have presented, we can achieve a conversion of the feedstock to biofuels around 48%. With a minimum fuel selling price between 0.9 and 3.4 euros per liter. And then there is a greenhouse gas emission associated, and these are only fossil-based greenhouse gas emission associated to the process, which is around 37 kilograms per CO2 equivalent per gigajoules of biofuels produced. There is some future work that we still aim to do in this project. One is do a more analysis considering different blends of urban waste, and also there is a potential of reducing the capital cost of the HTL production plant by introducing the membrane filtration technology in the water treatment of the HTL aqueous phase. So, and this is also an analysis that we would like to do. So now this has been my presentation, and I will be happy to answer some of your questions.
Thank you so much, Gonzalez. That was really interesting, and hopefully a positive aspect for today when we, like I said before, when we see how expensive our petrol is now, at least we can think positively for the future that we'll have an alternative. Okay, great. And so we've had some questions here. We'll start with Sinan from Bitlis Yeren University. Okay, so we've got three questions here. So the first one, it says that it's made from waste and its approximate cost was 0.6 euros per litre. And he or she asked, have you had a chance to calculate the initial investment cost and operating cost of biodiesel production from waste oil in litres of biodiesel production?
Waste oil based on what technology?
I'm not sure this question. Let's just, have you had a chance to, so as part of your analysis, did you look at waste oils as well? All right, okay, so there's a question. Oops, slide number 11. Profit. Okay, sorry. Okay, Gonzalez. Gonzalez, sorry about that. Let's go on to the next question because it's not clear to what it's referring to. But the second question is quite interesting. You said that you use natural gas in the system. So have we ever looked at using biofuel that we've produced to use back into the system?
Well, in the decentralized, in the HTL, the decentralized HTL plan for production of biocrude, the only option that we have considered to to supply the heat demand, the net heat demand that is required, is by natural gas. The biofuels are produced, or in this analysis, are considered to be produced in a centralized refinery. But in the upgrading process, yes, we consider first the use of light hydrocarbon gases to supply the necessary heat to the upgrading process. And yeah, so there is no need of natural gas. The only required use of natural gas is for production of the hydrogen used. We assume that the hydrogen used in the upgrading process is produced from reforming of natural gas. So, and there is an associated consumption and greenhouse gas emissions. Okay,
great, thank you. Okay, let's move on to the next question now from Ignacio Segura. The question is, were the calculations of greenhouse gas emissions made with the emission factors of RED2? RED2.
The calculation of the greenhouse gas emissions. No, in this case, well, we have considered in these calculations the basically the CO2 produced in the combustion processes for the HTL plant, and then the CO2 emissions associated with the reforming of the natural gas to hydrogen. But also in the HTL plant, in the combustion process, when we consider the use of natural gas in the combustion process, so here we have used CO2 emission factors, which are given by the IPPC.
Okay, great. And another question from Ignacio, it says, at levelized cost, when you add recoveries, are you allocating phosphorus and nitrogen extraction costs to biocrude?
Well, the levelized cost of the biocrude production includes all the capital costs and operating costs, and also there is an income associated with the processing of the waste. There is a gate fee associated with processing the waste, but also there is when we consider phosphorus recovery, there is estrobite production, and there is an income associated with the estrobite according to market prices. But the separated nitrogen, the nitrogen separated, particularly in forms of ammonia used in this pure thermal pretreatment, is mixed and used in the combustion process. It's not further recovered. It's not further separated, this ammonia, and so.
Okay, great, excellent. We have a question here from Christian, although I can answer this because he's asking regarding the processed water, how is it treated? Now I can say to you, please tune into the next webinar in which we'll talk, our researcher from KIT University, Ali, will be talking to you about membrane technology and how to process and treat the water.
Yeah, but I can say that in the baseline design we have considered, the treatment of the HTL water is performing a mechanical vapor recompression unit. It's a distillation process, and this is the baseline design that we consider. Okay. The additional, there's an additional. It's possible, and it's been part of this project, to consider membrane filtration technology. But as you, Edma, said, so there will be a presentation specific on that, which will be the third webinar.
Exactly. Great. I've just seen the time. It's 11:15. There are a few more questions, so I'll just ask Gonzalo, are you okay to stay on for a little bit longer just to answer a couple more questions?
Yes, there's no problem.
Yeah. Okay, so yeah, we've had a lot of interaction this morning. So let's just look at the next one. So we've got one from Lucas. It says, thank you very much for the presentation. It was very nice. He said, I'm not sure, but have you considered the sludge as an income on slide 12? Is it income or a cost, he says?
The sludge is an income in this analysis. So we assume that the actually the decentralized HTL plant is located next to the wastewater plant.
Mm-hmm.
And then there is a gate fee associated with the sludge that is an income to the HTL plant.
Great, excellent. Silvio is asking if the data behind the project is available to the public at the moment. I believe it is not at the moment.
The result, well, I'm not sure. It's been the results presented here and very much in detail with all the process flow diagrams, all the assumptions, all the market prices for consumables, utilities, equipment cost, parameters. Everything is being reported. And it's open access. So, but I don't know when the European Commission will release these reports to the open public. So yeah. I'm not sure.
Just to follow up on that, Sylvia, this project, the Next Gen Road Fuel project, is finishing on the end of October this year. So there will be more results presentations and final events. So stay tuned and keep an eye on our LinkedIn page, and there should be more information about data availability there. Okay, let's just see if there's another question, otherwise we can wrap up. Okay, Rahul, this is question. He says, thanks again for a very nice presentation. Could it be possible to use the CO2 from HTL gas combustion to decrease greenhouse gas emissions?
Well, I think there is in the CO2 emissions. There is a biogenic fraction of the CO2 of the greenhouse gas emissions, and these are CO2 which are released as part of the gas phase from the HTL process, and also are associated with the combustion of the light hydrocarbons from the HTL process, included or containing the gas phase of the HTL process. These are biogenic. The result that I have presented for the fossil-based greenhouse gas emissions are only associated, as I said, to the additional natural gas required in the process.
Okay, and there's a couple of questions here from several people about the analysis of using different feedstocks. So obviously today you presented the cost analysis using urban waste, but as part of Next Gen Road Fuels, has there been any analysis, for example, using wood waste?
This is a future work that we would like to carry out. The analysis that I have presented today and all the cost analysis we have been doing so far in the project is being based on sewage sludge, mainly because sewage sludge is being used throughout the project as a feedstock during all the experimental work and all the experimental development of the different processes. And since the analysis, the techno-economic analysis relies much on the experimental results, we have been focusing on that. But it's true that the sewage sludge is the worst case scenario. It's the worst case by far. we can achieve much higher energy efficient conversion efficiencies from the feedstock to the biocrude with lower metal and nitrogen, sulfur, oxygen concentration in the biocrude by using, for example, bio waste and also demolition wood or waste wood is also is a feedstock that can lead to much higher energy conversion efficiencies and lower metals and sulfur nitrogen content. And then we expect that the final cost using those feedstock will be much lower than the Swiss sludge. And there is other considerations for example, the process can be simplified if we consider bio waste, for example. Phase separation might not be so complex. So there are different considerations, and we would like to do further analysis on that.
Great, excellent. Now, we have got more questions, but we've really run out of time now. So I'm just, I'll ask Gonzalo if maybe afterwards we can write some responses directly to these people that have asked questions. We'll keep a record here, and otherwise, if anyone has another question that they haven't answered now, you can send an email to me or to Etta Florence, and we can get that responded to. All the information and the recording today will be available on the Next Gen Road Fuels website, and it will be shared on LinkedIn, so you can re-watch that for any further information. And I'd just like to remind you again that this is number 2 in a 4-part series, webinar series, maybe even a 5-part webinar series, because the next one will be April the 5th about membrane technology and about treating the sewage waste or the waste of the HTL, the wastewater of HTL process. And then on the 17th of May, there will be a further more detailed presentation about turning the waste into the fuels, which will be presented by Steeper Energy, Tom and Cherith, who are involved with the actual technology that creates the biocrude. So thank you again, Gonzalo, for a really interesting webinar that's had lots of participants and a lot of questions and answers. And well, everybody, I wish you a nice day. We'll speak to you soon. Thank you.
Thank you, Emma. Thank you all.
Bye.